Bueno, muy buenas tardes a todos y todos. Good afternoon, everyone. Welcome. Bienvenidos a esta actividad que hemos denominado hacia la metrología de 2050 con el JCRB. Mi nombre es Gabriel Molina Castro, soy funcionario del Laboratorio Costarricense de Metrología y seré el anfitrión el día de hoy, el moderador. My name is Gabriel Molina Castro and I will be the host in today's activity. Iniciamos con dándole la bienvenida a todos los que están presentes en la sala. Muchísimas gracias por acompañarnos y a los que están de forma remota también. We want to give a special welcome to our special guests and talkers here tonight, this afternoon. Mr. Martin Milton, the director of BIPM, Mr. Robert Gunn, responsible for NPL's international strategy. Welcome. Mrs. Marina Gerswolf, team leader from Frequency at Time Group at NRC. Mrs. Victoria Coleman, lead technical committee chair at APMP, yeah. Ms. Lerato Tatamala, senior manager from the National Meteorology Institute of South Africa. Welcome. Mr. Nikita Sviagin, okay. Head of the International Department of the Mendeleev Institute of Metrology from Russia, and all the other members of the RMOs participating in the JCRB meeting. Welcome all to this activity. Un saludo especial también para el director del Laboratorio Costarricense de Metrología, Fernando Andrés, que preside esta actividad, al presidente del CIM, señor Javier Arias, que también nos acompaña, y a todos los representantes de los laboratorios designados que están por aquí, miembros del Laboratorio Costarricense de Metrología y miembros de otros organismos del Sistema Nacional para la Calidad, que también fueron invitados. A todos una cordial bienvenida. Entonces, antes de iniciar las charlas del día de hoy, tenemos unas palabras de bienvenida del director Fernando Andrés Monge. So we have some welcome words from Fernando Andrés.
Well, I was not sure if talk this in Spanish or English, but to respect our guests, I will just do it quickly in English. I just want to say welcome again. Thank you for taking your time and being here present, and thank you for taking your time to do this activity. I know this is outside the JCRB scope. We did a great work early this morning and all the day yesterday, and a lot of things were accomplished for the sake of international metrology. But as I say, I would like to thank you for also transferring knowledge to the Costa Rican metrology community, here represented by people from our staff, people from the designated institutes, metrology professors too, colleagues, welcome. And I just don't want to take more time and just want all to take advantage of this opportunity. It is an honor to have the director of the BIPM, Dr. Martin Milton, in our institute and in our country. And I hope this is a great evening.
Thank you very much. Gracias, don Fernando, por sus palabras. A continuación, iniciaremos con las charlas que estaban Martin Milton, quien es el actual director desde el 2013. Su charla tratará sobre el plan estratégico del BIPM para los próximos años. So we welcome Dr. Martin Milton for his talk. So, Dr. Milton, the floor is yours. This one. You can pass it.
Thank you. So thank you very much. The DIs. It's been fascinating visiting your labs, seeing what's going on. I'm sorry I didn't get to see the DIs, but I saw the chemistry and the physics here, and it was fascinating. It's great to see how much you're doing and how much things have developed very recently, I think, for you. So thank you for that. We came here for a JCRB meeting, and I really hope that in the future, when JCRB meetings come to visit countries and institutes, actually a little symposium like this would always be part of the agenda, because I think we want to be involved in passing on things we know and triggering discussions and questions about things that we're involved with so that we can leave some knowledge transfer when we go. So a few words from me, really about highlights of work that we've done at the BIPM. So I start with some highlights of what we do in our 4 laboratory departments. The first laboratory department is our physical metrology department. Like you, we call it physical metrology. And in that department, we have mass measurements and we have electrical measurements. The mass measurements, the centerpiece now, is our realization of the kilogram using the Kibble balance. We have one of the 2 or 3 Kibble balances that's working more or less all the time now. We set a target uncertainty of 50 micrograms in 1 kilogram. We're a little bit below that now, so we're very pleased. We also organized the key comparison of kilogram realizations. We just did another one at the beginning of this year, and those are the key comparisons that determine the trajectory of the realization of the kilogram in this new system. So we also do mass calibrations. 87% of our member states, there are 64 member states now, have received mass calibrations from us since 2012, and now you're the 64th member state in Costa Rica, so we look forward to your calibrations coming when you need them. You can address me or the colleagues in the physical metrology department to access that. On the electrical side, we are very much concerned to upgrade our quantum standards to make transportable quantum standards possible and to make it easier for us to do comparisons at other labs. We've done that by looking at graphene as a potential quantum Hall resistance standard, making good progress with that, and developing new comparison schemes for AC voltage, which is something we've done as a project with PTB. 86% of member states have visited our electrical labs, and again, your DI in electrical is welcome to participate in our calibration scheme. I move quickly to time. Dr. Marina Gertzwolf is going to say more about time in a moment, but before she says anything, I want to show you my favorite picture. It's probably my favorite picture in metrology, actually. It's certainly my favorite picture in time metrology. So this chart shows you the contributions to the world timescale. That's the UTC, Universal Coordinated Time. These are the contributions from the different labs to that world timescale. So we see here at the bottom, the labs with the cesium beams, the oldest sort of primary standard. Then we see the area with the cesium fountains. More recently, there's a single rubidium fountain in Paris. And then right at the top, the bit that everybody is so excited about now, come in. The optical clocks, you see there in the chart out to 2018, not so much activity from optical clocks, but you see now in a version of the chart that goes to 2023, we're beginning to see significant contributions to the timescale calculation from optical clocks. So this is the diagram that gives us some optimism that an optical definition of the second is within sight and could usefully be implemented and support our world timescale. In terms of the consequences of those clocks to the timescale itself, they do result in improved accuracy in the timescale. In the time that BIPM has been organising the world timescale, the accuracy has improved from 10 to the minus 13 to 10 to the minus 16, which is about as good as it can be with the cesium fountain systems. In addition, the system is becoming more resilient as we have more labs around the world participating. Our third lab I talk about is our ionizing radiation lab. We carry out calibrations with high energy X-ray beams. Some of those calibrations we carry out on a nearby site because we can't afford all those big ionizing radiation facilities ourselves. And we're now also starting to do calibrations with another international organization, the IAEA, on their site in Vienna. That's a way for us to access a facility that is something that we don't have on site. We also work to provide calibrations, key comparisons of radionuclide measurements with our beta emitter measurement standard, the SIR, the International Reference System. This is the agreed ionization chamber that provides the reference values for all NMIs for radioactivity measurements. And then we have the transfer version of that, the so-called SIR transfer instrument that we use for short-lived measurements. Chemistry, we have a chemistry department. Actually, it's probably the largest of our departments, but I don't like to tell the head of the chemistry department that because it's very bad for him to hear things like that. But it's a little bit the largest. Anyway, we have work in the gas area and in organic areas. So in the gas area now, we have a facility for isotope ratio reference measurements. This is needed because until we got into the field, the area of isotope ratio measurements for carbon, which is very important for tracking carbon sources, so we try to understand the origins of the sources of climate change, there was no international reference standard for it. So we now have a ratio reference standard. We've done a key comparison with that already with 20 participants and 162 results, and it does perform to the expected uncertainty. On the organic area, we do work in terms of coordinating comparisons for pesticides in food, and here's an example of one of mycotoxin standards, which are toxic components in foodstuffs. We also did a comparison to support COVID-19 diagnostic measurements amongst the small number of NMIs who have got capabilities to measure COVID-19. And then we continue with work to support diagnostic measurements. Support for laboratory medicine is another big field for us, and we do some laboratory work there to support comparisons of diagnostics, such as for diabetes diagnostics and treatment. The chemistry department is also very directly involved in knowledge transfer activities. We have online courses on the use of FTIR, which we're now transferring into an e-learning course on FTIR. And we also have online courses on the characterization of organic CRMs. In terms of capacity building, a chart I showed the JCRB earlier, all of the regions take a good participation in our capacity building activities. Our capacity building includes online activities, it includes workshops based in our facilities in Paris, and it also includes laboratory-based knowledge transfer, either based with secondees or with colleagues working online and then transferring standards. In the capacity building area, we're particularly grateful to a number of NMIs, there's 9 there, who particularly supported us with support for specific capacity building interventions. We're, as an international organisation, one of the unique things we can bring to the metrology world is the ability to liaise with international organisations. A big piece of work, very successful, that we did last year was to hold a big conference with the World Meteorological Organization, the Metrology for Climate Action Conference. That conference resulted in a very interesting report with 120 agreed recommendations for the metrology community. Please take a look at that. It's on our website. I think it provides a roadmap for some of the interventions that NMIs might make in the climate area. Related to that, we've been accepted as an official observer at the COP meetings. We'll be going along this year with the intention of understanding the best way to have an impact at the COP meeting in 2024 or 2025. In particular, of course, the COP is a way for us to get impact and profile for what's been done with the Climate Action Conference. Other work we've been doing with international organisations includes promoting the case for World Metrology Day to be recognised by UNESCO as a World Day. I strongly expect that this is going to happen in October or November this year, but we always have to wait for the member states of UNESCO to vote, which will happen this year. We've passed all the stages and we see very strong support for the proposal at the Executive Committee. This would mean that the 20th of May 2024 would be the first World Metrology Day badged as a UNESCO World Day. Other liaison activities we've done with IOs, we liaise with UNIDO and were influential in the document on quality infrastructure for sustainable development. We work a lot with our partners at OIML, including on the joint publication on national metrology systems. We've been working with the OECD with their initiative on international regulatory cooperation, and we work a lot with the ITU to support them, and they support us on the promotion and use and dissemination of UTC. In terms of digital transformation, I think we have another talk on digital transformation, so I won't say too much. We've done a lot of work recently to understand the requirement for digital transformation and then put in place the programs in the BIPM headquarters that are going to support the NMI's best. We had a big workshop in 2022 for 600 participants, which really helped CIPM see the scale of the issues. We did a survey amongst the consultative committees. We've now put in place programming interfaces to allow direct digital exchange with the key comparison database, with the time department database, and also with the reference frequencies for the realization of the meter. This is only the beginning. The next step is what we call the SI reference point, which is a single digital reference that captures all of the information in the SI brochure. So in summary, we've only got 69 staff, 23 PhDs. We hold a lot of meetings, 640 days of meetings in the period up to the last conference, more than 400 calibrations, nearly 700 participations in our own comparisons, 2,700 participations in capacity building actions, and 670 users from 115 countries in our e-learning courses. So that's the end of my very quick summary of some of the things we do at the BIPM. Thank you for your attention.
Thank you very much, Dr. Milton, for your talk. I don't know if there's any questions or algunos comentarios, preguntas con respecto a la presentación del señor Milton. No? Okay, so thank you very much again for your talk. Bueno, damos seguimiento entonces a la serie de charlas que tenemos programadas para el día de hoy. Pasamos con la participación del señor Robert Gunn, quien es el responsable del desarrollo e implementación de la estrategia internacional del NPL del Reino Unido y de los programas de investigación metrológica que desarrolla esta institución en conjunto con Euramet. De hecho, la charla del señor Gunn en esta oportunidad trata sobre las oportunidades de capacitaciones e investigación que hay tanto en el NPL como en Euramet. So, Mr. Gunn, the floor is yours. I'm just going to help you with this. Yes. Okay.
Thank you. Well, good afternoon, ladies and gentlemen. I see the weather has changed a little. Unlike my colleagues who've popped in for a few days, I've actually spent a week here enjoying your wonderful country before I came to this meeting. So you'll get plainer slides because I wrote it in Monteverde, but it's written with feeling. And what I've tried to do is talk to you about some of the opportunities for the international community to work together on various things. I'm here for the JCRB meeting where I come wearing a Euramet hat as the chair of the Interdisciplinary Metrology Committee for Euramet. But as you said, my day job is head of the international office at MPL. So I've split my talk, and I will talk partly about things where we can do things with Euramet provides opportunities to work together, and part what we're doing at MPL. So I'll start with the Euramet bit because they're the ones who brought me here. Euramet's obviously the RMO for Europe, and I'm pleased to say that all of the other RMOs, except GulfMet, have a formal liaison agreement with Euromet. I wish I'd brought this slide up earlier when I had GulfMet on the screen, because we could try and plug that gap. Our technical committees collaborate with those of the other RMOs to deliver the CIPM MRA. And I know that other RMOs are often invited to participate in our training activities and other capacity building and knowledge transfer. I hope that some of you have had the opportunity to do some of that. The thing which distinguishes Euromet really from the other RMOs is that we have the benefit of some European metrology research programs where we get funding from they're jointly funded between the European community and the member states who are participating. We've had a series of these in succession. So we started off with the European Metrology Research Programme. That was way back about 2000 or so, and that was 400 million euros. The Commission told us that we were only going to get one programme. This was our lot, but as soon as we started the programme, we started on the process of persuading them why a 7-year programme wasn't going to be enough. We'd need to do more. We needed to continue. We needed to follow up. And we persuaded them. We got MPIR, the European Metrology Programme for Innovation and Research, with more money. And of course, they told us that was the last chance we were going to get. We weren't having any more money. So we made a good case and said, metrology is important. We can do lots of things that will help you. And we convinced them. And we currently have running the European Partnership on Metrology. We didn't get the extra money, it's the same size, but it's another 7 years. And we are now in the third year of the programme, third call. And it will not surprise you if I tell you that we have a working group. And at the Board of Directors meeting next week, we will be considering the paper that we will submit to the Commission for why we need a follow-on programme, because this one will not be enough. And metrology is far too important to stop now. You need to carry on supporting metrology. But the characteristic of these programmes, they consist of an annual 2-stage call, and they have a range of themes. Those have changed a little over the years, but basically they fit into SI units, fundamental metrology, the energy or environment, healthcare, support for industry, new one coming in now, digital metrology, which of course is going to be very important. A normative programme, this is what metrology we need to do to support international standards. And research potential, which is how we build up the capacity building for helping institutes to develop a research capacity as well as just a calibration facility. And there are opportunities for you all to participate in EPM. So the first stage call, what they call a call for proposed research topics. And it opens in January each year. And it's open for anybody in the world to put forward needs for collaborative metrology research. They need to fit certain criteria, including considering where we get most of the money, a potential for beneficial impact on more than one European country. But of course, if something benefits every country, that fits. You have an improved chance of success, I have to say, if you're putting your idea in partnership with European NMIs or DIs, partly because that helps convince people that there's the European benefit, partly because they've been doing it for years, they know how to play the system. The second stage calls come out for project proposals come in June. So we're currently on the third call. NMIs and DIs from other regions can participate in consortia bidding for projects. you're from a country which is classed as low and middle income countries, you're eligible to receive EU funding, as are also any countries associated to Horizon Europe. For example, New Zealand. I believe Korea is possibly trying to get associated also. There is a certain irony here because from the UK, where I come from, we are currently not associated, so we are a sort of bit on the outside. Though next year we will be back in. The announcement from our government that we were going back in came about the same time as I was writing this in Monteverde. In fact, it wasn't in the first draft. It was added on the second day. And I'm pleased to say that we have already had participation by labs from all regions, including GulfMet. So all regions have participated in European metrology research programs, one of the three codes. And I would very much encourage you, if you have opportunities, please do join us. They are a great way to learn from others, to bring the knowledge that you have, and to help to build a world metrology community. I'll now swap and put my MPL hat on rather than a Euromet hat. So again, MPL participates with our international colleagues in the consultative committees, in Euromet's TCs. We are associate members of APMP, so we have a contact person in all of their technical committees. We participate in the European metrology research programs. As I've just said, with UK association now agreed, we will do that even more strongly. We also engage in bilateral research collaboration. Sometimes that's formal funded projects. Sometimes it's alignment of mutual interests. We have schemes for secondments. I'll talk about these more. And we have opportunities for students. In 2021, we published 12 roadmaps for research, what we see as the highest priority research areas for metrology. This is based on a foresighting exercise that we carried out, consulting people throughout our laboratory, but also throughout the UK, and also some international experts. We didn't ask them what do you need for metrology. We tried to look at, well, what are the needs of society? What will governments be looking at to answer their problems in 2030 to 2040? And from that, we then work back and say, well, what are the technologies that are leading? What will be the metrology that we need to service those technologies? And these roadmaps show that critical metrology that we think needs to be put in place over the next decade. And also it highlights, well, what are the measurement challenges and the barriers that we're going to have to overcome? And the reason that we've published them is that we hope they're going to stimulate collaboration and inspire scientists from around the world to join us and create innovative solutions to overcome metrology problems. So this is the list of the 12 areas that we've published roadmaps on. Kilogram, obviously the kibble balance is a major feature there. The Kelvin, again, as we move towards acoustic thermometry, trying to get away from the ITS 90 and to the proper temperature scales. One I know that you're going to talk about later, redefinition of the second. Digital metrology, that's impacting all of us as we try to do things differently. Medical physics, healthcare is a real key issue for governments, and there is a lot that metrology can do to help in that area. Climate change, again, affects everyone across the world. There's masses of things that metrology can do. Also linked to that, the net zero energy. Advanced manufacturing. How can we make things better, more efficiently? Biometrology. I think the bios, we've seen the growth in chemistry. If we look at the CCs, the one which produces the most activity is CCQM, the chemistry. They're also bringing in the biology. Who knows? At what point do we need to set up a new CC for biology to break out? Not yet, I don't think. One day. Quantum electrical metrology, again, an increasingly complex field. Quantum clocks, sensors, communications, quantum computing, very much things which certainly our government is interested in. And a key message which I would give to all of you is, if you want to get funding for metrology, do the things which your government finds important, because if the government finds them important, they will give you money to do them. So find how you can support your governments in doing what they want to do, because then they will help you do what you want to do. And this is just one example of the roadmaps. This one's actually the net zero energy one. I don't expect you to be able to read that from where you are. The important bit to notice is we have a time scale from 2021, at the time we were writing them, to 2031. The white column, well, that's what we were doing. We know how to do that. That's easy. We're doing that. The green bits, we're pretty certain we know how to do those. We haven't done them yet. We're pretty certain we know what to do those. The red bits, they need doing. We're not quite sure how to do those yet. So, any ideas? Get in touch. We can get there first. So these are openly published on our website, and we are very much open to the idea of anyone who wants to work with us. That's where we think we need to go. If you think we're wrong, we'll be interested in the conversation on that as well. Secondments. We have two schemes at MPL. The aim of both is to facilitate building of relationships with partners and to focus and nurture links between individuals and between the individuals and their labs, because those kind of relationships are a real benefit. So we have two schemes. One requires links to MPL's NMS programs. That's our government-sponsored programs. The other is a newer scheme which we've just established in memory of my predecessor, Kamal Hussain, who was our previous international director, and that's more going to be focused on innovative and curiosity research. Schemes are open to technical people for research, but also to people in NMIs who are not in the technical areas. If there is a benefit of exchanging experience in the management and non-technical aspects of how we develop metrology, then we're open to those as well. We can have people coming over to MPL, and we can have MPL people coming to other labs. The secondments can be from 2 weeks to 6 months, and the main scheme provides the costs of travel and subsistence, and the newer scheme will also cover the time of MPL staff while they're doing the secondment. But if there are opportunities that you think you could benefit from working, make the relationship with one of our scientists, find an idea where you can work jointly together, and we can process the applications. And finally, training and PGI is our postgraduate institute. So we do various bits of training. Increasingly, our training is done in an electronic online form. There are a number of courses currently, I'm going to say they're available on our website, A lot of them are free, so if you want some training, dig into our website. I'm very much working to try and get them available through the BIPM portal and through the Europe. We've had a few technical issues of getting compatibility, but I'm working on it, and I hope they will all. I hope a good number will come through that route. But so at the moment they're there and they're available, and I hope they get the wider distribution route that BIPM will provide. We also have a postgraduate institute. MPL has about 1,200 staff, and we also have about 200 extra researchers each year. Most of those are students doing PhDs. And some of them spend all of their PhD at MPL. Some of them spend all of their PhD at a university, but they have a supervisor who is at MPL. And there's a good number who are in between. They spend some time at MPL in our laboratories, sometimes at the university. As well as their PhD research, we try to give them a good education in metrology and business and what it's like to be in a lab. Most of those at the moment, I have to say, are with UK universities. But we are open to arrangements with overseas universities. We have one example that we have already done with where we worked in partnership with in Metro in Brazil and São Paulo University, and a student from São Paulo associated with Metro did some work, did his PhD associated with our kibble balance. Real unfortunate thing was, having got it agreed, he was going to spend a lot of his time at MPL. Of course, COVID came along, so he did most of it in Metro. But we are very open to the idea that if there are arrangements we can make where a student from an overseas university is perhaps associated with an NMI in Costa Rica wants to do their PhD, can work through our PGI, come back fully trained to work here. It's the sort of arrangement we can do. I'm hoping that we will get some. We are already talking with some of the other NMIs who have similar sort of arrangements. We are talking with INRIM in Italy, who have a postgraduate scheme, to see whether we can do exchanges there. At some point, I'm going to be talking to my colleagues in Korea, because they also have an academy. And so an arrangement whereby we can benefit the training of young metrologists and give them the experience of working in NMIs, I think is a good way to build up international relations, build up networks, and improve the metrology community. So there are a number of routes there where hopefully we can build up some future collaborations. They won't all work at the moment. I'm well aware that Acamet is a little smaller than MPL, not quite as research focused, but there are opportunities to grow and come through and to develop. And we are very much open to trying to develop those relationships. And I hope to visit you all again.
Thank you very much, Mr. Gunn. I don't know if there's any quick questions for Mr. Gunn. ¿Alguna pregunta rápida que tenga el público?
I was wondering if this activity is only for PhD or can be made for all. You have.
Yes, what we can be looking at is the service economies will be open to some of this.
Bye, Mr. Gunn. Thank you very much. Ok, continuamos con las charlas. La siguiente sería la participación del señor Nikita Svyagin, ¿ya? Que es el coordinador del Departamento Internacional del Instituto de Metrología Mendeleev de Rusia, y su charla será sobre la visión de jóvenes metrólogos que tiene la organización Regional QMET. So, Mr. Sviagin, floor is yours. Sorry for my pronunciation of your.
That's not a problem.
This is right.
Yeah, that's it.
Okay, you just pass.
Okay, thank you. Good. Great. Good afternoon, everyone, once again. Yes, so my name is Nikita Zvagin. I am the head of International Department of NIM. Here it's written in Russian. And also I am the chair of Joint Committee on Measurement Standards in COMET. You can see the COMET logo here. And NIM, Dmitry Ivanovich Mendeleev Institute for Metrology, is part of Rosstandart, Russian Federal Agency for Technical Regulation and Metrology and Standardization. And here is the logo of Rosstandart. And I'm showing it because I will be talking about the initiatives from these three organizations and the initiatives that are connected with young metrologist activities. I'm also the part of the program by BIPM, program that is called Young Metrologist 2050 Plus, and I'm one of the coordinators. So today I will be talking about young metrologists and projects in COMET, projects in Rosstandards, and a little bit in other NMIs. So I will start from the activities in COMET, and we have one main activity for young metrologists. We have an international competition that is called the Best Young Metrologists of COMET. This competition is held once every 2 years in one of our institutes in member countries. And you can find all the information about it here. What I can have to mention is that representatives of other RMOs take part in every second competition. So this year we have the competition only for our COMET members. So the next competition will be open to representatives from other RMOs. So representatives from SIM and also from Costa Rica are, of course, very welcome. Generally, the competition is held jointly with some scientific and practical conference on metrology issues. All the procedure is written in our internal documents. You can find them on the COMET website if you wish. You can also write to me and I will show you everything that you need to participate. You can see some photos from that competitions of different years. Here is just to show you that we are taking it very seriously, and this is the evaluation criteria, how to evaluate the reports that our participants are given. As the real scientists, we even introduced the formula, how to find the best reports. This is the evaluation criteria that you will have to pass through if you will be participating in our competition. And here is some history. The 9th international competition was in 2021. It was held online because of the COVID, and we had some representatives from SIM, from Colombia and Mexico, also from Euromed, from Italy. The next competition was closed, so we had only members from our countries: Armenia, Belarus, Kazakhstan, Russia, Uzbekistan. Here are the winners: Ruslan Davlatov from Dnipro, Russia, and Sultanbek Smagulov from Kazakhstan. Here are their photos. So this is about the COMET young metrologists, and you understand that this competition is open for those who are working in national metrology institutes. These are the people who are already in metrology, who are already deep in metrology, but we have a problem that we need somehow to get people in metrology. And this is the second point that I'm going to talk about. I will now going to talk about the Rosstandart initiative for creating, let's say, trying to keep people in the metrology and trying to invite people to metrology, let's say like that. So the next one is that slides. Don't be afraid of Darth Vader. He is here on the good side. Yes, so this initiative is called Metrological Education Cluster of Rosstandard, and this is the federal system for popularization of metrology and early career guidance for children starting from kindergarten, from the combined effort of schools, colleges, universities, some additional educational organizations, companies, and authorities in all regions of Russia under the coordination of Federal Agency of Technical Regulation and Metrology. It is designed to help schools and universities in career guidance for school children, employment of students, as well as in improving the competencies of specialists solving metrological support problems. We are creating some different events. You can see here their photo from one of these events, and of course to raise interest in young people, we are using some let's say interactive formats, some playful formats. You can see here we are even asking our friends from other planets to help us. Yeah, so metrological educational cluster includes a lot of different organizations. You can see here totally it's 172 organizations in total in Russia. The headquarters of the metrological educational cluster is in St. Petersburg, in Nîmes, in my institute, and from that institute we are trying to coordinate all the work of that organizations, 17 regional clusters and members of Russian Federation, 5 kindergartens, 70 schools, 42 metrological classes. I will show them a little bit later. A boarding school for students of the Ministry of Defense, Children's Railway, 5 organizations of additional education, 7 colleges, 32 universities, and 33 organizations and companies. Some logos of that companies are also presented here. What are our main goals in this initiative? To increase the number of college applications for standardization and metrology. There is the percentage that we are trying to reach in the future. We also want to increase the Unified State Examination passing score. This is the score that the school students get after graduating the school, and this score is used to get to some university, and depending on that score, the student can choose the specialty that he wants to have in the future. So we want, of course, metrology be more popular, and we want to increase that score. But there is also some nuance that I will talk about later. There are some results of our work in 2022-2023. We had 223 events with more than 9,400 children taking part. We got a significant increase of number of state-funded places in State University of Aerospace Instrumentation, restoration of that degree that is about standardization and metrology in Volgograd State University, some state-funded places in State Transport University, and many more. So what is the formula of success of that program? It is a new form of introduction of school students to the future engineering profession, and our metrology educational cluster turned out to be a simple and convenient solution for educational institution and industry enterprises. And it doesn't require large financial, organizational, and personal costs. So what helps us? The trend towards revival of engineering professions in our country. This is the good way for early career guidance. And metrologist career is universal. It has a big demand in industry, business, science, and civil service. And also talking about that Unified State Examination score, it is now low because metrology is not very popular. So people with some low score can go and get easily to metrology, and then they are in the metrology, we can take them and keep there in the metrology for the whole life. They will understand that metrology is really a very interesting science and a fundamental science. Also, it's a project of federal agency, as I said, and it has a great status and opportunities. So schools need fresh ideas for specialized classes. I will talk about specialized classes a little bit later. And cluster provides opportunities to hold city, regional, or federal level events. That is also very popular in Russia. Here you can see logos of different schools, of different colleges and universities that are participating in that program. And talking about the metrological classes, these are the overall of all metrological classes that we have in Russia, and this is the classes which with metrology in their name. So you can see that even in the first grade, so these are children of about 7 years, yeah, we have 6 classes with the metrology in their name, so they are already coming to school and starting metrology from that ages. When I was 7 years old, I think that metrology is something about temperature, yes, and forecasts. But now we are making it like that, and you can see that there are some very good metrological classes in our country. And that's all about their force in our country. I just want to show you that in Comet region, not only we are working with our young metrologists. For example, Cost Standard, who is now the holds the secretariat of Comet, and the director of Cost Standard is now the president of Comet. They also have some initiatives, and since 2022, the Republican School of Physics and Mathematics have been holding effective classes in metrology and standardization, and also students have participated in some events and also had a talk with Gabit Mukhambetov, who is the general director of Cost Standard and now the president of Comet. And some practical trainings were conducted to demonstrate the process of calibration of measurement instruments, where students participate directly in measurements. And also some academic competitions and scientific projects on topics of metrology are organized in order to interest students in this field, etc. So this is the brief information about how we are trying to get some new metrologists, and I hope so that maybe some people from that photos or from the photos that you have seen before, maybe in 20 years or maybe even 10 years, some of that people will be standing like me and telling people about how metrology is cool and great to be the part of it. So thank you for your attention.
Thank you very much, Mr. Sviagin. I don't know if there's any question, alguna pregunta para el señor Sviagin. No? Ok. Perfecto, entonces continuamos con las charlas del día de hoy y seguimos con la participación de la doctora Marina Gerswolf, quien es la líder del grupo de tiempo y frecuencia del NRC de Canadá, y su charla tratará sobre la redefinición del segundo y sobre la continuidad de la UTC. So, Dr. Gerswolf, sorry, the floor is yours for your presentation. Okay, so you can pass it.
Hello, everyone, and thank you for the opportunity to present this exciting topic on the redefinition of the second. So I have an ambitious title for the SI second and UTC for today, and tomorrow I'll try to present what's happening on this topic. So as I was introduced, I'm the team leader for frequency and time group at NRC, but here I am also attending JCRB meeting as the deputy technical chair for SIM. So nice to meet you all here. And I also participate in CCTF activities and the chair of the working group on TAI at the CCTF. So SI system, you know the history. The meter convention was signed in 1875. We're going to celebrate 150 years soon. The international system of units was defined in 1960. And in 2019, just recently, we had the redefinition of the system to go from artifacts and the units such as kilogram and ampere to the base constant. And you can see them on the inside circle. So you must have all seen this, nice circle. What I want to point your attention to is that the most important unit here is the SI second. As you can see that in all units except the mole, really, the realization of all of these fundamental units in SI second requires the definition of delta nu, the frequency, which is the inverse of the second, which is the definition of the SI second. So I'm very proud to be working in this field, and I just want to raise the importance of this area in your eyes. So what about the SI second? It was defined by the CGPM resolution in 1960 as a fraction of a tropical year. It was an astronomical second. There is a full definition here written there. Then in 1967, this was already redefined using the atomic clocks, cesium atomic standards, and the specific frequency, transition frequency in a cesium atom of a hyperfine transition splitting was now used to define the second and has been used ever since. And this happened because the atomic clocks provide much more stable realization of a regular oscillation than astronomical observation and the rotation of the Earth around with respect to other celestial bodies. And in 2018, just recently, the definition of the SI second didn't change, but the wording changed. In accordance to all the other units that are now defined with fundamental constants, the wording for the SI second was changed from this middle bullet to the bottom one. I'm not going to read it to you. You can find it on the BIPM website. You can see here the illustration of the first cesium atomic clock built at NPL in 1955. So the measurement of frequency and time is a fundamental research topic which rewarded researchers with many Nobel Prizes. I'll just mention them quickly so we can see how impactful this topic has been. So the cesium atomic clocks really became possible thanks to the finding by Norman Ramsey of the split resonance measurement, which immediately increased the sensitivity and the resolution of the measurement of the transition frequency in the cesium atom and allowed the clocks to be very accurately measured and be evaluated with high precision. That was necessary for actually building a stable and accurate clocks. This illustration is from NRC archives at National Research Council in Canada. We have been building these clocks, and you can see the different generations of the clocks of what I found in the archives. You don't see cesium 1 here, must have been started earlier, but these are the cesium 3, 5, and 6 that used to operate at NRC, and the cesium 5 clock that you can see in the middle. It was the official frequency standard for Canada, and what it was at that time one of the most accurate clock in the world. Of course, they have been since then all surpassed. These are thermal beam clocks. They've been all surpassed now with the new technology. So a few years later, a few Nobel laureates later, the technology for laser cooling and trapping of atoms has been developed, which allowed to introduce even greater accuracy in the measurements of the SI second and the measurements of the cesium clock transition, because now instead of a thermal beam of cesium atoms, you could cool down a cloud of atoms with lasers to the temperatures below around 1 microkelvin. and then also use these laser beams to launch the atoms up through the microwave cavities. So they fly up and then fall down under the force of gravity. This is why these clocks of this type are called fountains, because they operate like fountains, like water in a fountain, which introduced with the fact that the thermal movement of the atoms has been greatly reduced, and the time it takes for the atoms to go through the microwave cavity once and then go through it for the second time has been increased an order of magnitude, which of course increased the resolution of the clocks by an order of magnitude. So this is an example of a fountain clock at NRC that we operate at NRC. This is an AutoCAD drawing, but it's actually a working clock that is that we have been running almost continuously for the last several years. So the optical clocks, the frequency standards. The optical clocks. We're still in microwave clocks. So the cesium clocks, their primary standards. We have uncertainty budgets need to be evaluated, and you can see that we have this cluster of representative uncertainty measurements for the cesium clocks, starting from the appearance in 1950s. And you can see that there are two different groupings of these clocks. So the first line that averaged them down with our improved accuracy measurements, these are thermal beam tube clocks, the ones I showed you the photographs of the big apparatus that shoot the atoms from one side to the other. But then a second grouping of the cesium clocks, these are fountain clocks. You can see that they have a much better, much lower uncertainties, but the improvements slowed down. They were not as fast over the years. The improvements slowed down. And at the moment, the fountain clocks that operate around the world achieved the ultimate accuracy limit at 1 or 2 parts 10 to the minus 16. But once the cesium clocks were developed, the microwave transition is in cesium clocks, that's the clock transition, is used with greater accuracy that we have now. The researchers around the world realized that if we were not using a microwave transition, but an optical transition instead, we could gain orders of magnitude in accuracy, because if your probe frequency that you use to measure the transition is microwave, but optical, it's terahertz. So immediately you get 5 orders of magnitude improvement. Here is an illustration. I'm showing the energy diagram for cesium clocks and for an example of an optical clock, which is a strontium ion clock. So a few Nobel Prizes later, optical clocks were made possible. So we have a Nobel Prize for development of the ion trap technique, for the pole trap, with the illustration here of an NRC trap design. We have a Nobel Prize for the development of ultra-stable lasers and the comb frequency, optical comb frequency technology that actually enabled the measurements of transfer of measurements of the optical clocks from the optical domain into the microwave and RF domain, which is necessary to actually make use of these clocks. The clocks that we want to get 1 pulse per second. So you have to get this optical frequency comms technology that would allow for that. And another Nobel Prize, and the optical clock is built. So these are optical clocks, new type of frequency standard, new system of systematic shifts, frequency shifts that need to be evaluated. The shifts are a little bit different, and they're different for different clocks. This is just an example described here. The interesting thing about optical clocks and that there are many different candidates, and many research national metrology institutes and universities, they started working on different species that I listed here. They have their different frequencies of their transitions. These are illustrations of traps. So this is focusing mainly on this illustrations more focus on single ion clocks. And so different designs of the traps, different lasers that I used, different uncertainty budgets, pros and cons for every single clock here. And what I want to point out is, if in cesium tube, thermal beam tube clocks, you had an oven with cesium atoms and a small pinhole, and the whole cloud of cesium atoms comes out. Then fountains, you have a cloud of atoms that you cool down to a few millions of atoms, and they're very low temperature, have better uncertainties. with optical clocks, you deal with a single particle in ion clocks, for example. You trap a single ion in a trap, and you measure the frequency, the transition frequency of the single ion, which I think it's quite an amazing achievement to trap a single particle and work with it. So these are examples of the clock that are operating around the world based on different species. So this is the graph you've seen before. These are microwave clocks. So then when the optical clock started getting developed, those are the circles in red and green. First, the accuracies, of course, were not as good, but you see that the improvement in accuracy was drastically faster than the improvement of the cesium clocks, and they surpassed the accuracy of the cesium fountains in 10, 15 years ago, and now they surpass the fountains by 2 or even sometimes 3 orders of magnitude. And so when this happens, when your standard performs better than your measurement instrument and your ruler, you need to redefine the second. So the realization that the second will not remain with cesium came relatively early on. When the optical standards started surpassing cesium, the frequency and time community realized that we have to move toward the redefinition. We have to start preparing for it. So if you redefine that, if you have this superb frequency standard with much greater accuracy than currently available, there is great potential for future development in science and technology. And here I'm listing some of the fundamental research projects that would benefit greatly from getting access to the clocks, to the frequency standards with stabilities of 10⁻18 and 19. So optical gravimetry, quantum networks, fundamental constant stability, actually whether they're constant or not constant. This is what you always need the clocks for. So as I mentioned, the idea that SI second has to be redefined came in early, and already in 2017 at the CCTF meeting, the roadmap, one of the first roadmaps for redefinition was initially proposed, that illustrated here. And when we develop a roadmap, we have to decide when we redefine and what are conditions that need to be satisfied to allow for the redefinition. So this was the first attempt, and you can see here there are different categories of what has to be achieved before we can proceed with the redefinition. And it had an ambitious schedule, and it was hoping to have the redefinition. I think on this slide it shows that it will happen in 2026, so maybe even 2024, but I don't think we're there yet. So the work within CCTF continued, and the time and frequency community continued. And in 2020, CCTF prepared a more updated roadmap with conditions in different areas, better identified and formulated. A consultation with the time and frequency community across CCTF happened, with a survey coming out for NMIs, given the opportunity to provide feedback about what they thought about this condition, how they were included. And you can see here that the conditions divide into mandatory and desirable. So the top part of each of these illustrations is the mandatory conditions, and the bottom part are desirable. So we would like to achieve that before the redefinition happened, but it's not necessarily 100% necessary. So you can find details about these conditions for the redefinition in an article that's been submitted just recently to Metrología, but it's available on the archive. I'm giving a link here, and this actually lists all these conditions that I showed you in the previous graph. And so the red are mandatory, blue are desirable, and so they're divided into different categories about actual performance of the frequency standards, the performance of the comparison techniques, because if you have an excellent frequency standard in Americas and then another one in Europe, how do you measure them one against each other? So you need to have a measurement technique that would be compatible or better than the accuracy of the standards, the uncertainty of the standards. So these are the conditions, and CCTF working group, task groups are monitoring the performance of these conditions, and this is these are mandatory, all the mandatory criteria listed here from the previous slide, and this is the fulfillment level. This is from 2022, and so the idea is that all the mandatory criteria are at the above the 90 percentile vertical axis when we redefine the second. So you can see that some of these conditions are close to that target. Some already surpassed it, but there are a couple critical ones that are not there yet at all. And so, for example, the validation of the OFS accuracy budget frequency ratios is the second one. This is not there. And what is validation? And validation is exactly the comparison of standards to each other, the measurement of the frequency ratios between different standards, or the measurement of this standards, measurement of the same standard in one lab compared to a lab in the same standard built in another lab. This is a table from presentation from Patrizia Tavella. I borrowed for her CPM. Key presentation is of the auxiliaries. These are desirable conditions, and also they are also going to be monitored. And you can look at them. For example, one of the desirable one would be nice to have commercial optical frequency standards. This will greatly improve the acceptance and acceptance of the new definition in the industry if you can buy commercial standards. So that's a desirable condition, not mandatory. So, okay, well, we assume that we meet all these criteria. By the time of the redefinition, all the labs are working really hard to try to achieve this goal. But now I showed you in one of the earlier slides that there are many different optical clocks, optical frequency standards. There was a whole table and pictures with different standards. So how do we redefine? With cesium, it was cesium. Now we have 10 different options. So there are actually 3 options for the redefinition. One is an ideal one would be if we followed all the other SI fundamental units, and they would be defined through fundamental constant, like the kilogram is defined through the Planck constant. So this would be the ideal approach. Unfortunately, none of the fundamental units are known to date with the precision required to match the accuracy of the existing clocks. So it would reduce the accuracy of the realization of the SI second by 4 orders of magnitude if we were to, for example, to define it through fixing the mass of the electron. So this option for now doesn't work. We don't want to reduce the accuracy, we want to improve it. The second option is sorry, this was option 3. I mixed the order. So the fundamental constant is option 3. Okay, that will not work. There are other options based on a similar approach like it is with cesium. We'll pick optical frequency standard and say this is the new definition of the second. So there are 2 possibilities. One is option 1. We pick one species out of this whole ensemble available, which is the best species, and we define the new second based on this unit. So this is a good and clear approach. The only challenge is that there are many candidates. There are technical reasons to pick one, and there are political reasons to pick another, and everyone wants to have their species to be picked. So it's not going to achieve a consensus easily. So option 1 is one of the options that have been considered. But option 2, a more interesting one, and option 2 actually has option 2A and option 2B. Option 2 is based on, we're going to use all the knowledge that we have available right now. We have all the different species that have been measured. So the definition of the second, the new definition of the second, will be based on their weighted average and every clock, optical clock, will be able to contribute, and its weight will be based on its uncertainty and the frequency ratio measurements with respect to other standards. And we define the second this way. So this is option 2A, which says these are the standards, optical standards we're going to use, and these are the weights that we assign to them. And so the average value n calculated once, and that is the fixed definition. But what happens if we find out that there are some systematic errors that we didn't take into account? So this doesn't allow for this solution doesn't allow for changes, for easy changes in the future, because you will have to follow up the redefinition process. So there is the potential for option 2B, which says this will be a dynamic definition. We're not going to fix the species and we're not going to fix the weights. We will evaluate them, I don't know, once a year, reassign the weights, recalculate the new frequency, the new value of the average, and this will be a moving definition of the SI second. This is conceptually a difficult idea that maybe international metrology community as a whole may not be ready to accept this. I personally like it because I'll tell you my view. Why I think it's good because it allows for NMIs to continue research into the development of different types of optical standards. It wouldn't stop. It wouldn't force. Because we all have limited resources. It will not force management of NMIs to say, no, now we stop everything. We're going to build just the standards that are part of the definition. It allows for fixing the errors. If, for example, some of the measurements turn out to be off by I don't know, few sigma from the defined value, it allows for the corrections to be made in the system for these values to become to be corrected and the weight average to be moving to be following the best realization of every standard. It also allows for the clear winner to come out essentially. So, for example, we have an ensemble right now with weights maybe equally distributed between the clocks because they have similar uncertainties, but a nuclear clock comes on. A nuclear transition, which will be 2 orders of magnitude better than the optical transition, it will automatically get a weight which is much higher than everything else. Essentially, the definition will follow the best clock that comes out as a winner. So this approach allows us for continual improvement and research, but it's fundamentally, it's very different from what we are ready for right now, because it means that the SI second is changing. So if you want to use it maybe for long-term observations of fundamental constants, maybe it's not the most convenient solution and right solution. But I invite you, this is a link to the same archive paper. The pros and cons, the SWOT analysis for this different options is presented there. It's a very interesting read, and I invite you all to read it. So I think I went through this. I went through this explanation without showing you this slide. So this is 4 orders of magnitude decrease in the accuracy, option 1, with the fundamental constant like mass fixed. New definition might rapidly become obsolete if we pick one specific species and we made a mistake. It didn't turn out to be the best species. And if it's an ensemble, then we can. It's a conceptual deviation from the constant, from the current definition, but this is maybe the way to go forward. So as I showed you before, we have mandatory criteria. One of them is to actually compare standards to each other and make sure that they agree within their uncertainty, their frequencies agree within their stated uncertainties. And it's not easy to do because our current methods that allow us to compare clocks, the most common one at GPS, the accuracy is at the 10 to minus 17 level, maybe. And we need something better than 10 to minus 18. So fiber links are the alternative method. And the only difficulty is that getting access to fiber links is very difficult in some countries and impossible in others. In Europe, they have been very successful in using, and they have access to some fiber links for research networks. So this is just an example of from European publication about one of their projects. They also have this huge funding that that we just heard about, and hundreds of millions of dollars, which allows them to actually pursue these measurements. So we're not there yet, but research is ongoing. One of the alternatives to fiber links there are free space links, that optical links that allow for some comparisons, but the limit is hundreds of kilometers. So maybe they'll go to the satellites and back. That's the research field. Another option is transportable clocks. So there are many labs around NMIs working now on optical transportable clocks. So the system that can be moved from one NMI to another, and you make a measurement with the required uncertainty levels. These are the different clock comparisons to fulfill this I 1.2 mandatory criteria. This is the slide that Martin showed. So you can see here, I'm showing it here. This is one of the criteria is to have regular contributions to TAI. So they've started. There are not enough of them, but they're not running as continuously as desired, but it's growing rapidly. So this is the roadmap plan for different scenario for the redefinition. I think the first option with the redefinition is 2026 is unrealistic. We are not going to meet the mandatory criteria by that time. We're targeting the second one. So in 2026, we already know which way we're going. And the redefinition actually happens in the 2030. And the 2030, everything is ready. And we're happy with the results of all the criteria achievements and the choice. And if it doesn't happen, then we have to postpone to the next CGPM by another 4 years. So these are the plans. And the CCTF working very hard to stay on schedule. So there were task forces running between 2020 and 2023, 3 task forces that I'm listing here, and with their chairs, and they focused on surveying the liaison stakeholder communities about their views on the redefinition and their interests and potential contributions to redefinitions. They looked at another subgroup looked at what are the different options and different frequency standards, and what are they, what is available and what accuracies are there. And the third group looked on the comparisons and the dissemination techniques for optical frequencies and the timescales. And some of the work that has been accomplished is listed here with the Metrología paper that summarizes it all. And of course, the important outcome of this work were the CGPM recommendation number 5 and resolution number 5 in 2022 that accepted the roadmap as the plan for moving forward. CCTF work continues. The task forces that have been slightly rearranged, renamed with more targeted and focused work, and we have now a task group with redefinition options. So the ones I prepared for you, they have to keep on working on that. The task group on the redefinition criteria that is going to monitor all this criteria and keep an updated status available to the community. And another working group is on the education to actually tell everyone what is the redefinition is about and how we can make use of it and how we can promote the adoption of the new technologies in this industry and the research community. And so these are the planned work for this task groups. I'm switching gears now. So we talked about SI second. The SI second is a frequency measurement, frequency reference. Now we'll use frequency a lot in every SI unit, in many of the measurements we have. But the UTC is the time scale with the unit of second, SI second, but it is a standard time scale, internationally accepted time scale, and is the time scale for everyone to use and actually synchronize their life and events against each other. So UTC, Coordinated Universal Time, this is a schematics. It's a time scale that is maintained and disseminated by BIPM. It's a paper time scale. It means it's a report that comes out once a month, and it's based on the submission of data of the measurement results from the atomic clocks that run in all the NMIs. That are 90 of them, and there are almost 600 clocks that submit their data weekly and daily to BIPM to calculate the pre-atomic time scaled and corrected with the primary and secondary standards to generate the TAI. And the TI is the time scale in unit of seconds, the atomic time scale. And then to get from TAI to, these are the illustration of the primary, secondary standards that contribute to the TAI. But TI is not UTC because there is a big difference between TI and UTC. The unit of time in these two scales is the same. It's the SI second. But UTC is different from TI by leap seconds. The leap seconds are introduced at different times, as you can see here in this graph from the time the UTC was the atomic second was defined. And it's based on the deviation between the atomic time, which is measured with atomic clock with cesium standards, and the astronomical time, which is the Earth rotation with respect to other bodies. And so, because the Earth rotation is not as stable, we can see that it's leap second is introduced with different frequency to the TI timescale to generate UTC. To keep atomic time and astronomical time aligned. So we're talking about improving our S-second measurement from 10 to minus 16 to 10 to minus 18 level. And at the same time, we have these jumps of 1 second that happen every few years and disrupt operations everywhere, especially now when we have such a digitized and connected world. So leap seconds have been a sore point for timing community for quite some time. And they caused a lot of noise every time they introduced. This is again from Patricia's website. She collected here some summary of news reports on how different services, financial services, telecom services were disrupted the last time the leap second was introduced. And also that it looks like maybe a negative leap second will have to be introduced in the next few years because the Earth rotation suddenly changed the speed of its acceleration. And so BIPM, and so there is a risk of, the problem with leap seconds is that these jumps disrupt computer systems that need synchronous time. And big telecom companies and big internet companies such as Google, Amazon, Microsoft, Alibaba, they introduce their own solutions, what to do with the timescales when the leap second comes in. And it means that there is a proliferation of different timescales. They're not synchronized to each other. They are not UTC timescale. And this is a risk to the metrology community and to the international community as well, because these timescales are run by private organizations, well, private or industrial, not government organizations, not the democratic community like time and frequency when UTC is generated. So BIPM has been working hard with ITU to come to a solution of relaxing this requirement that UTC timescale is aligned with UT1 time, which is astronomical time, within 1 second. There were several iterations to this process. It's been running for many, many years, but just recently in the 2020, the Memorandum of Understanding was signed between BIPM and ITUR. That memorandum defined who is responsible for what. So BIPM is responsible for defining the second. ITU is responsible for formats of how it should be disseminated and broadcast. The CGPM Resolution 4 in 2022 was about on the use of the future development of the universal time. It talks about the specific topic of increasing the tolerance between UT1 and UTC before or on 2035. And so the next step is the ITU World Radio Conference that will happen in November this year, where we all hope that they will also pass through the, I don't know what it will be called, the resolution, a decision that the decision on the alignment between UT1 and UTC is with the BIPM and out of the scope of responsibilities of the ITUR. And With that, I thank you. This is my end of my presentation if you have any questions.
Thank you very much, Dr. Directo, for your presentation. I don't know if there's any questions. ¿Alguna pregunta? Oscar, Marina, if you can talk to the mic. Oscar.
How much time do you consider it to take to have a optical commercial realization? Because in some cases, some countries, we are not able to make such research work. Maybe that could be a solution for atomic clocks, according to your experience.
So I think it's possible. It's doable. You told me today that there are some commercial companies that claim that they will have them for sale in the near future. I think that, well, it depends on several factors. I think the technology is approaching there to make commercial devices. You need the several parts. You need the laser systems. That's known and available. You need the vacuum systems and that's also known and available. So you have just to package everything together. You need frequency combs because you need actually the clock with the comb accompanying it, so you can transfer the optical frequency into the microwave and RF domain. So that's also becoming more readily available. Nothing really precluding from building a commercial standard and having it running continuously. It's one of the considerations, one of the topics that was discussed during in the task groups that I presented to you at CCTF. So whether identifying a specific species as the new standard, would it help push the development of commercial devices? Because now the industry will know what has been selected, and they will put all their resources in building commercial devices into this product, or not, because maybe the best clock for the realization of SI second may be not the best clock to build commercially. For example, I spoke mostly here in the illustrations that I had were ion clocks, but lattice clocks that are based on trapping neutral atoms in a lattice of electromagnetic potential wealth. So you have more atoms trapped at the same time and have better signal to noise. They may provide much better accuracy because they will have lower uncertainty. They might be harder to build as commercial devices because they're just more complex physical systems. So so the commercial systems devices may go and pursue the development of other species that are just more robust and lasers are easier to build and obtain. So it's not clear. It's not clear to me. But, so I don't have an answer for you, but I think that they will come. The optical standards will come in a matter of 5 years, maybe. That's maybe my prediction.
In terms of traceability, which is something of the most important in terms of the DMC services, because most of them get the estimation and the traceability for local UTC realization. Do you consider that which can be your advice taken into consideration when the realization comes?
So it's a good question, and in reality, the situation for majority of the labs will not change, because the SI second now is defined with cesium. Only the cesium fountains are really the clocks that are primary standards that can be fully evaluated and can realize the SI second. All other clocks, including cesium commercial clocks, are secondary standard. They can achieve their traceability by measuring them against another clock, but they cannot be fully evaluated for systematic shifts, and so they are not primary standards. When the second is defined with, let's say, strontium ion, because that's the clock we have at NRC. So in that case, people who operate fountains, the fountains now become secondary standards. They will have an extra component to the uncertainty that will be due to the measurement against the primary one, which will be minor the expectation that will be minor compared to the uncertainty of the fountain itself. The people who operate hydrogen masers will continue to get the same traceability as they have right now. Masers are not primary standards, they're just very stable oscillators, but you get traceability through continuous measurements against SI second, through published it with the UTC or against a standard that the people operate in the lab. If you have cesium commercial clocks, they will still provide you essentially with the same uncertainty. The difference will not be relevant to this type of standards, because we're talking if the cesium second defined now with fountains 10 to minus 16 level, with an optical standards it will be 10 to minus 18 level. The commercial cesium clocks are 10 to minus 14, 15 maybe, but that's it. Yeah. Yes.
No. I know that the stock market several years ago used a link with some clocks because there are some transactions that are doing by machines. I don't remember the name, but it's fast.
Yeah.
Thing.
High frequency trading.
And how the stock market deals with the interaction of the lipstick? They complain, I know, but they have to solve the problem. So, do you know how they solve the problem?
I think they solve it differently. From what I remember, I think some stock markets just close down for an hour around. Yes. Well, not all of them. So some stock market and certain are closing down. They are okay. The simple answer, I don't know exactly, but they are using. So there are different options, and that's one of the problems. They can synchronize their clocks to GPS time, for example. GPS time doesn't have leap seconds. It runs continuously and it runs away from UTC with every leap second introduction. So if they all synchronize the time to leap seconds, to GPS time, they don't have leap seconds. If they all do it correctly and if all their devices, their GPS discipline servers are all configured the same way, this will work and errors happen. The other option is they synchronize to Google time servers over NTP. And Google has a leap second smear, which I think is they change the duration. They don't have leap seconds, but they change the duration of the second, the actual frequency. They change it for a period of, I think, 24 hours around the leap second. And so to not to have a jump, so and to maintain the sequential timestamping, which is a problem because if you have in one system timestamp with that the system was synchronized to Google time, another one synchronized to GPS time, you have you don't have synchronization between these two systems and they're completely off. Yeah.
Two links specially dedicated to FPL.
Right. So they are
synchronized not to GPS but
to yes, and this is what we as metrologists want to do. We want everyone to be synchronized to UTC because that's an international reference time scale, and it will ensure that everybody and everything is on this is synchronized to each other. And if we get rid of leap seconds, this will ensure that essentially because there will be no reason for Googles and Amazons to invent something new because UTC is there and it's stable and reliable. So that's that's a problem that we hope that will be resolved soon. Thank you.
Thank you very much.
Thank you.
Perfecto, entonces, muchas gracias a la doctora Gertrude por su charla. Continuamos con la actividad con la participación de la doctora Victoria Coleman, quien es la líder del Comité Técnico Regional de APMP y que forma parte del Instituto de Metrología de Australia. Su charla abordará los tópicos de caracterización de nanopartículas. So, Dr. Coleman, welcome. The floor is yours. Just going to help you with the presentation. I believe it's this one. Yeah. You can just pass it, please.
Great.
Thank you, and good afternoon. I want to thank Fernando for nice hosting this week and also for the invitation to speak today. I'm going to talk to you with two different hats on. Firstly, with my hat as the section manager of nanometrology activities at the National Measurement Institute in Australia. And then I'm going to give you some information about activities around nanoparticle characterization in APMP, and more broadly, some of the materials metrology activities that we have in APMP. But before I get started, just a few words about NMI Australia. We have about 320 staff. We cover chemical, biological, physical, and legal metrology. We have about 200 scientists, and the area that I work in, which is nanometrology, is located in our physical metrology laboratory. We are currently 5 staff. So for us, and I think more generally, there's some generic drivers about why we're interested in nanometrology and why we want to make accurate and reproducible measurements, particularly at the nanoscale. And that ranges all the way from the sort of product development end through to quality control to assist manufacturing, to help with trade, meeting regulations, because in some jurisdictions there are regulations governing the use of nanomaterials in products. And I guess the more interesting aspect for nanomaterials is the safety aspect, or the social license to operate. And accurate measurements in this area give us also informed choice. And so our laboratory at NMI Australia covers this kind of broad aspect. We help industry with measurement services kind of across this range for all of these different endpoints. So we have 3 main activities in my group. The first is development of a primary standard for dimensional measurements at the nanoscale. We do that with a metrological scanning probe microscope, a type of atomic force microscope that we've designed and built in-house. And we use that to link basically the meter to measurements we make on the nanoscale. Then we do a lot of measurements by atomic force microscopy, looking at different materials. We look at things like imaging forces, how imaging may deform particles or systems, and we look at a lot of new sort of 2-dimensional materials with that system. And then the third area which I'm going to focus on today is work we do around accurate nanoscale measurements, particularly for particles suspended in liquid, to support a whole range of different activities. And some of the recent projects we've been involved in have been looking at, for example, how titanium dioxide, the pharmacokinetics, so how it's processed through biological systems like rats. We're doing that in conjunction with our nuclear safety organisation for food safety applications. Increasingly, we're looking at microplastics and ways we can support measurement of microplastics in the environment, in food, and in biological systems. And we also look at a range of different sort of more metrology aspects of really understanding the instrumentation in our lab and getting to know how we can best apply it. We do a lot of work directed at standards development, particularly through ISO TC229 and ISO TC24. So that's nanotechnologies and particle characterization. And we're quite heavily involved in an organisation called VAMAS, which does pre-normative standards development. And these two systems work quite well in harmony to develop accurate and reproducible methods for nanoscale measurements. So when we talk about particle characterization, we're really talking about a whole range of different endpoints, essentially, that can control or influence properties of materials at the macro scale from the nanoscale. And that covers really a wide range: shape, size, concentration, size distribution. And really, we start from sort of very theoretical, simplistic systems, kind of in the center, where we have, spherical particles, all of the same composition, pretty high in concentration. These sorts of things are quite, we have quite robust methods now to make these measurements. But as you kind of move out that scale and you move to low concentration materials or more challenging shapes or higher aspect ratios, multiple size distributions, multiple compositions, things get a lot more complicated. And so we really need to understand our measurement systems to really make sure that we can measure really accurately on those scales. So we do this with our nanoparticle characterization laboratory at the National Measurement Institute in Australia. We cover a lot of endpoints. It was great earlier this week. Brian organised a visit for me to Nanotech, where I met Sergio, and saw a lot of similarities between the work they do in their lab and the work we do in our lab in terms of helping to both make direct measurements on materials to support industry, but also to help with solving measurement problems. So one of the key things that we spend a lot of time doing in that lab is really what I call demystifying so-called black boxes and really understanding the assumptions that are being made in a whole host of, I call it common instrumentation that you might find in any laboratory for characterizing nanomaterials. And some of the most common instrumentation are things like dynamic light scattering, particle tracking analysis, separation techniques like field flow fractionation, differential centrifugal sedimentation, and electron microscopy. And we study these instrumentations to really understand how or what the measurement or the measurand actually is in these systems and how it's influencing the results that we get out of those systems. So one of the biggest challenges, I think, for nano is really understanding what is actually being measured by these different systems. And a really good example for that is if you can compare or think about a system of gold nanoparticles with, two different sizes, a 100 nanometer gold particle and a 20 nanometer gold particle. And in different types of instrumentation for nanomaterials, you measure in different modalities. So you might have a technique like electron microscopy where you're imaging particles. It's a number-based technique, and you're essentially sizing on every particle. Or you might be using a light scattering technique, which is very sensitive to scattered light intensity, where you're really looking at an intensity signal. Now, if you go back to consider the difference between a 20 nanometer particle and a 100 nanometer particle, if you're using a single particle technique like a microscopy, you will get equal peaks if you consider them by number. But if you use a technique like dynamic light scattering, you need something like 15,000 20 nanometer particles to give the same signal as one 100 nanometer particle. And that kind of challenge is really poorly, I think, understood, particularly in the industrial community or the research community. And so if you were trying to produce, say, a sample of particles of 50 nanometers for a particular application in nanomedicine, you could be completely missing a population of particles depending on the technique that you're using. And if you have smaller particles present in that system, it may disrupt the function of the nanomedicine. So it's really important to get that right. And this kind of intensity versus volume versus number-based measurement is basically what's often the output or the y-axis of your measurement instrumentation. And although it's possible to convert between these different sort of populations, it introduces a lot of uncertainty. So you really need to get your head around that and understand your measurement system. The second point I wanted to make is that when we talk about particles, often people go straight to particle diameter. And not all diameters are equal, particularly when you think about real-world particles where you often don't have a perfect sphere. So nearly all the measurement instrumentation would assume that you have some kind of spherical system. And these assumptions of sphericity are based basically on different aspects of the particle. So you might have a sphere you might determine an average sphere by electron microscopy, which could be very different to the hydrodynamic diameter that you could measure by another base technique. And this gets even more pronounced once you move to sort of more exotic shaped particles like, rods. So, as I mentioned, we apply this work a lot, or these different technique bases, to work that we do through organisations like VAMAS and ISO. And I just wanted to illustrate here the link that we have between the work that's done at VAMAS, which is basically pre-normative standardisation research, and that then goes on to inform documentary standards development. So within VAMAS, we run a lot of interlaboratory comparisons to really nail down methods for accurate measurement of materials. And the example I've got on screen here is for measuring titanium dioxide particles by electron microscopy. This round robin was conducted through a number of labs across the world. The results were published in a paper, and then that paper basically formed the basis for an ISO standard. And so that forms a really nice workflow of how we can improve the rigour around measurements of particle sizing around the world. The other big key for nanomaterials is certified reference materials. We really, or industry and other users really need these to support validation of their instrumentation. And so we've worked quite a lot in supporting the European Commission in development of a range of their nanoscale reference materials in silica and titanium dioxide. And the interesting thing about these reference materials is they come with technique-dependent values for their particle size. And so that means you can use these methods for a range of different, these materials for a range of different techniques to really be sure that you're understanding your measurement system and understanding the results that are coming out of those measurement methods. So switching now to some of the work that's been done through APMP. APMP actually ran one of the first, I think the first global comparison on nanoparticle size, which was started in 2013 and piloted by CMS ITRI and NMIJ in Japan. And this was I guess, quite an innovative comparison for its time, where we looked at 5 different nanomaterial samples and measured them with a whole host of different techniques. And when you do that, you see quite some technique interdependency for the results that were generated. So we worked really hard as a community to understand what was going on, understand what those differences were, what the uncertainties were, and look at ways that we could basically correct for those changes to try and achieve a so-called global reference value for the particle size of the different materials. What we discovered through that process is that although we were able to mitigate some of that technique variability by doing things like correcting the AFM measurement results for uncertainty of particles placed on surfaces, you can't do that for something like a dynamic light scattering result. That's a clearly different measurand. And so that was really quite a useful, the first kind of metrology approach to particle sizing and published through the Technical Committee of Length and then into the KCDB. So this activity was really driven out of one of APMP's really unique technical committees. So within APMP, we have a Technical Committee of Materials Metrology, which is really an interdisciplinary committee that focuses specifically on metrology for materials properties and measurement, particularly those that have so-called method-dependent measurands. And originally it was established as a working group in APMP, but it became a full technical committee in 2012 under the then chair, Dr. Seung-Jae Cho from CRIS. And this committee brings together a variety of experts within APMP, and we perform supplementary comparisons and then link with a relevant TC to bring those through to the CIPM. So, for example, the comparison I showed you just before, we linked with the Technical Committee of Length and through the CCL to deliver that comparison. And also the TCMM within APMP has a formalised link with VAMAS, and that's a really strong way for VAMAS to also ensure its own metrological basis by linking with an organisation like APMP. So TCM is quite interesting because it brings together a range of experts from across the Asia Pacific who have quite different drivers. Some of our members are really strong in the semiconductor industry. They have very flourishing semiconductor industries in their economies. We see health, safety and environmental aspects for nanomaterials as another big driver. Production of advanced materials and emerging materials like graphene is really important. And that kind of blend of interest and that blend of expertise is a really powerful way to attack these sort of multidisciplinary problems. So, yeah, I kind of already made the point, but that kind of diversity of committee, we don't have a direct linkage. And so we work hard to partner then to bring our results through to the CIPM MRA. So basically, in summary, nanoscale characterization as a field is definitely maturing. There's been a lot of advances in recent years for benchtop instrumentation, but there's still a lot of measurement challenges, particularly as things get more complex and more interesting. There's really a very large market for nano-enabled products, particularly around nanotherapeutics, nanomedicines. COVID-19 vaccines, for example, are a nanomaterial. There's a lot of use in cosmetics, veterinary medicines, agricultural products, and a whole range of also composite materials. So really, the key to this work is helping to support industry, I think, to innovate with high quality and confidence. And to do that, really, it needs to be done in concert with the development of reference materials, reference methods, and documentary standards. And that's also really important then for us as a metrology community to ensure that we have the accurate metrology to support those developments. So that's more or less all I wanted to say, and wanted to thank you for your attention.
Thank you very much, Dr. Coleman. I don't know if there's any questions. ¿Alguna pregunta para la doctora? ¿No? Okay. Thank you very much. Perfecto, entonces continuamos con la participación de Miss Lerato Tatamala, ¿ya? Quien es Senior Manager de Gobernanza del Instituto Nacional de Metrología de Sudáfrica y que nos dará una charla sobre los programas de seguridad alimentaria que se mantienen en AFRIMEDS. So, Ms. Tatamala, the floor is yours. That's going to help you with your presentation. Oh, this is not it. Oye, no está la presentación, está repetida. Es la 7, pero la 7 es la misma de la 5. Just a few minutes. ¿Dónde está el JCRB? Sí.
Vaya aquí. Ahí. Este.
Okay. Perfect. So, all yours. You can use the.
Thank you very much. Thank you, everyone. As they've already introduced me, my name is Lerato Ndatamala. I'm the Secretariat for the Technical Committee for Quality, and I'm the Senior Manager at the NMISA for Governance, Risk, and Compliance, with the background of chemistry and engineering physics. So I'm going to be taking you through the food safety capacity building training that we have within the AfriMIDS, and then that is sponsored by the German Corporation and the PTB. So this is also happening at the NEMISA Training Center, but it supports the overall AfriMIDS activities. So within the African continental free trade areas, there are risks of food supply, because if you look at the African continental free trade areas, it means that the borders are going to be opened for trading, and then wherein food will be one of those that will be used for trade, and then also trying to avoid technical barriers to trade based on the poor quality of the products that will be traded within the country. So in 2021, there was a need from AfriMIDS wherein it was proposed that as the regional metrology body, we should have a food testing capacity building that will be in a form of a project that will be divided into 2 phases. And that will be for assisting in the trade and other things that I've already alluded, and also strengthening the local testing capacity. So that was very necessary. So the phase was broken into 2. And then the first phase was to make sure that we have the Pan-African survey to assess the food safety testing capacity within the AFC FTA and identify the gaps associated to that. So the survey was conducted, and then most of the metrology, well, they participated, and then we got the results back. So on the results, they reported the highlights on the specific training needs to support the gaps that were identified during the survey. So training was one of those, so that food can be monitored and then being consumed at a safe status. So what was highlighted, those specific training needs to support the food monitoring and the inspection, and also the ISO IE 17025 accreditation. So these were covered in the first phase. So in the second phase, it is the phase that came in 2023, which is the year that we are in for training. So the training initiatives, like I indicated on the previous slide, is supported by the German Corporation, is also supported by the PTB, and takes place at the NMISA in South Africa. So the objective of this program that I'm putting on is to build capacity within the NMIs within the region, and to develop the NMIs, to the developing NMIs and the DIs with the necessary chemical analysis metrology skills to suitably deliver services in support of food safety and quality within the AFCTA. Remember, this is coming from the survey that was conducted throughout the RMO. So it is a responsive to that. And also, the project that is going on, it is aligned with the African Union Food Safety Strategy for Africa for 2022 until 2036. So this is more on the prioritization of the protection of public health, and also for economic growth. If you can see, like after pandemic, things were just somehow. So this was one of those things that were put in place as a response, actually, to assist in the economic growth, and also to enable fair and safe trade within the region and globally. Remember, I indicated that one challenge is for technical barriers to trade, wherein there are those technical And then there are some measurements challenges. So this one also came up as a resolution to the measurement needs, so that metrology measurements can come as a solution to help the region. So this training and capacity building, there are specific areas that was looked at. So the scientists from NMIs, they are open for this training, and also scientists from the developing NMIs, and then the DIs within the African continental free trade areas, they are open to attend to that. And also the major national food monitoring and inspection laboratories that play a key role in the maintaining of food safety and for food quality, they are also encouraged to attend these established courses. So the training courses that we have the on-site training courses, and we also have the online, we have the proficiency, and then we also have the on-site summer school. So if we can look at the first one, the on-site one, we also do the instrument maintenance, the operation of troubleshooting, especially on the GCs and GCMS, on the LC and the LCMS, on the ICPS, OES, and on the MS. So these are the on-site, so that we do have the laboratory facilities where in the practical part of it will be showcased to the participants. And then we also have the on-site summer school, where in this training on the mycotoxin, on the pesticides, on the toxic elements, on the nutrients, and how to develop and validate methods and reports. Because you can do all this analysis and everything, but if you can't use the validated methods, if you can't also be able to know how to report, that's going to be a challenge as well. And then we also have the interactive online session, which also has some practical. This is more on the chemical metrology, on the traceability, on the uncertainty of measurements, on method validation, sample analysis and assessment. There's also a full workshop on that. And then there's also training on proficiency testing schemes, wherein is also on the mycotoxins, on the pesticides, on the toxic elements, and on nutrition. So there's also demonstration for continued competency, because those who are, I think we all have like an accredited, and we have submitted our CMCs. There is a need for metrologists and other scientists and engineers to continue demonstrating that they are competent on what they do. It's not a once-off thing. So this also support that. Like I indicated here, like the trainings are offered at NIMISA in Pretoria in South Africa. So there are those that are available online. If you can be able to be there, they can also be offered online. So I think we have a schedule for 2023 and 2024, wherein we have different activities, and then here we've indicated the number of days and some of the days, the possible days that are planned, wherein we offer like maximum of 10 participants per course, so that when we go for practical, we can be able to accommodate them in our laboratories. So we have like on the instrumentation, we have the gas chromatography, liquid chromatography, and the inductively coupled plasma spectrograph. So these are, I think, the dates. Yes, we still have some for the next year, and then even for the remaining of this year, if you can do some follow-ups, there can be some that can be tailor-made and prepared. And even on the food analysis, there is practical training, where again we take a maximum of 10 participants for food labeling, on the protein and sugar analysis, for the toxic and nutritional elements in food, mycotoxin analysis of food and feed, and pesticides analysis and fraud. So this is like under the summer school group. So like I said, on the on-site courses, there's also an opportunity for hands-on training, wherein you'll be operating the instruments and being taken through the whole process. So the fees here, this is the fee structure, which covers 2 weeks, and then is sponsored by PTB. So meaning if they're interested in training, they can just arrange their own travel, own accommodation, on spend and stipend. So I can't go through the next slides. They also show like the schedules and other things. So if you go to the AFRIMES website, That's where the list of everything and the plans is displayed. So this is continuation for the schedule for the food contaminant analysis, where we have the theory and the practical, and also the feedback workshop on the pesticide in organic solvents. So these are like 1 day, 1 days, and then they're virtual, meaning anyone can attend from their own countries. And then there's also theory on the determination of pesticides in fruit matrix and practical thereof, and then feedback workshop session. This is on the pesticides. So these are also the fee structure, which again, there's a 50% sponsor from PTB. And then the same applies here on the heavy metals, and then also on the veterinary drugs. They are also offered there. And then this also continuation, but if you can look here, is on the chemical metrology. It's just a switch, a combination of most of a pack. That will be a virtual course, which is an online, and then you can also see the fee structures there. And then on the proficiency testing scheme, also there is a participant there. We also assist if maybe the NMI, they are planning to get accredited on ISO 17025, and also again on 17043 and 17034, we offer that. And then if maybe you have a current scope that you want to expand, you can be taken through. Maybe if there's some parameters that you are not even comfortable with, there is an offer to take you through the process. And then some people, they go through accreditation, they get accredited, and then maybe after 18 months, they lose accreditation, they lose scope, but they don't maintain that. They fail to provide continuation of competencies on that. So we also assist in maintaining the scope so that you don't lose your CMCs, you don't lose your parameters. And then again here, the PT's participation and delivery is 50% sponsored by PTB. Like the rest, the training will cover like the remaining 50%. So all this information that I'm presenting here is available on the AfriMed's website. And then for more information, you can contact the training center, which is available on this email address, training@nemisa.org. So maybe addition to this, I only covered the chemistry part of things because we're talking about food safety, but there are other offers in all other areas that if like there's a need for such, some are tailor-made, some are already available. When I say in all fields, like including like both the physical and then on the medical metrology, like including the acoustic, vibration, ultrasound, gas, both on the gas preparation and on the CRM for the gases. And then also the force, torque, and hardness, temperature, humidity, pressure, time and frequency, and also on the mass and quantities and the volume, and on the photometry and radiometry, and then also on the fiber optics, on flow, and on the radioactivity standards. So those are just some of the courses that can be prepared and offered apart from the food safety one. So this was my last slide, and thank you very much.
Thank you very much, Ms. Tamala, for your presentation. I don't know if there's any questions, alguna pregunta. Yeah. So, diga la duda.
Are this training open for other regions or only for Africa?
It's for the regions and for other articles, because we've been offering to the countries like Indonesia and other people out.
Thank you very much. Perfecto, entonces por último, pero no menos importante, tenemos la última charla del día, Last Presentation of the Day, a cargo del ingeniero Olman Ramos, quien es el jefe del Departamento de Metrología Física de la COMET, y que nos hablará sobre certificados digitales y los procesos de digitalización que se han hecho en el Sistema Interamericano de Metrología. Entonces, Olman, adelante. Nada más te abro la presentación. Listo.
Buenas tardes. Muchas gracias por esperar. Thank you for wait at this time. Trataré de hacer la presentación lo más breve posible y trataré de mezclar un poco de español. And I will try to make some English with Spanish and maybe make faster. Okay. Lo primero, ¿qué somos nosotros? El Laboratorio Costarricense de Metrología es el laboratorio nacional de Costa Rica. It's the National Metrology Institute of Costa Rica, created by law. And, nosotros tenemos esta estructura interna desde el punto de vista técnico. Technically, this is our structure internal, divided in 3 areas: chemical metrology, legal metrology, and physical or physics in this area here. Algunos de ustedes visitaron los laboratorios el día de hoy. Today you will go to this, was in our laboratories, so you know how here inside this institution. En 2005, el Laboratorio Costarricense de Metrología firmó el acuerdo de reconocimiento mutuo y ya en 2022 somos miembros plenos del Buró Internacional de Empresas y Medias. In 2022, we was the member state, thank you, of the VIPM. Para aclarar un poco el contexto del título que nosotros escogimos, seleccionamos, el Sistema Interamericano de Metrología es parte de los organismos regionales del Buró Internacional de Metrología. So, the International System of Metrology is part of the VIPM, is part of the RMO of the VIPM. And if you know, we are very here, this part, a little bit. El Sistema Interamericano de Metrología ha trabajado desde el 2018, principalmente desde 2019 en adelante, en el desarrollo de un grupo de trabajo para el desarrollo de las actividades en digitalización, que es el grupo 14. Este grupo está dividido en diferentes task forces de trabajo. Se incrementó el desarrollo de estas actividades a partir del 2019, principalmente por el problema de la pandemia. As you know, in 2029, at the end of 2029, thank you. The pandemic was a problem, so increased the development of digital investigations inside the different RMOs in the world. Por esta razón, pues se creó el grupo 14 y los task force que aparecen acá son los que están en este momento trabajando y están activos. Para el desarrollo de las actividades de estos task force se han pues inscrito y realizado diferentes proyectos, principalmente con financiamiento del BID, del Banco Interamericano de Desarrollo. 2 de estos proyectos están ampliamente vinculados. El primero es Metrología para la Transformación Digital, para apoyar los servicios de salud en América Latina y el Caribe, que se divide en 2 partes. El desarrollo de una plataforma digital para que los clientes puedan hacer una solicitud de los servicios, que esto es digitalizar la forma en la que se interactúa directamente entre el laboratorio y los clientes. A esta plataforma la llamamos el Portus, que la está desarrollando el compañero Fabio acá, que a mi lado izquierdo. Y otro es un proceso de automatización de la captura de datos para condiciones ambientales con el uso de los diferentes equipos de condiciones ambientales que nosotros tenemos aquí dentro del laboratorio. En la primera parte, en el desarrollo del Portus, también se está trabajando en el desarrollo de un certificado digital de calibración. La otra parte que se liga a este primer proyecto es el desarrollo de un termohigrobarómetro con criterios digitales. El termohigrobarómetro, que lo podemos ver aquí, representado. Principalmente lo han desarrollado los laboratorios que tienen la capacidad de crear un poco de electrónica y vincularlo directamente a la metrología o a las mediciones, a sus laboratorios, a sus capacidades. En nuestro caso estamos creando 4 que tienen 4 tipos de sensores diferentes, entonces se calibran esos 4 tipos de sensores diferentes. Muy importante, que es lo que nos trae aquí también, que es la parte de metrología, que metrología 4.0 es más que una definición, es el concepto en donde la ciencia de las mediciones interviene para proponer parámetros adecuados para la representación correcta de la información asociada y trazable al sistema internacional de unidades, incluidos métodos, herramientas, representaciones y expresiones de cantidades, unidades, errores de medición e incertidumbre de la medición para que los datos y los metadatos sean entendibles y de uso para las máquinas. Tiene que ver con la sintaxis, la semántica, la taxonomía, los vocabularios controlados, las ontologías y todo aspecto que se caracteriza y da sentido digital a los datos y metadatos asociados a la medición. Leo la definición porque la definición es un poco compleja y tiene muchas partes. Entonces, lo que estamos haciendo, como les puedo comentar, es que nosotros como metrólogos aportamos conocimiento directamente con las actividades que realizamos, y uno de nuestros fines, the principal objective of our laboratories is provide traceability, make some measurements in different areas. So the metrology 4.0 is very important because gives some security to the people. This is the principal objective. En el caso de los certificados digitales de calibración, voy a tratar 2 temas. We discuss about two tasks. First, the DCC, and second, the digital DSI. En el caso de los certificados de calibración digital, bueno, pues la idea de los certificados digitales de calibración es que sean documentos electrónicos que aporten valor o que aporten datos o información asociada a los diferentes procesos de calibración que se realizan dentro de los laboratorios. Estos certificados, estos documentos están destinados a ser leídos, interpretados y usados por máquinas. The DCC will be used by machines, not for humans. This is the principal object. It's very complex to imagine that, but it's a real situation that is happening right now. La estructura del DCC contempla datos administrativos, resultados de medición, comentarios y documentos anexos. The structure for the DCC is administrative information, results of measurements, comments, or I don't know, information about the calibration, and extra documents that we need to include then inside the DCC. Se utiliza, por ejemplo, uno de estos documentos anexos es el PDF que pueden leer los seres humanos, que está escrito o se basa en base 64. Aquí pueden ver el enlace de la página del PTB, que el PTB aporta mucha información en un grupo de trabajo principalmente para el desarrollo del DCC. So here in the right side you can find the link to the PTB web, in where we find information about the DCC and the investigation right now of this DCC. Un ejemplo claro que tenemos sobre cómo se representaría la información en el DCC es un valor de temperatura. Here have a value of calibration in temperature with uncertainty, and the different normatives, or I don't know how to say in English, but en español sería más o menos como decir las diferentes límites, normas o referencias, the references, que nosotros necesitamos tomar en cuenta para incrustar o colocar esta información directamente en el DCC. For example, la ISO 80,000, the brochure of SI of the BIPM, the GOM, CODATA information, and something like that. All this information covered that all that we need to represent this number right there. This is a number that the human can read, can interpret, but a machine don't see that. The machine see this. This is a representation of the information of XML format. It's the same information like that, but this information is for humans. Esta información es para humanos, diseñada específicamente para que el humano la vea, pero para las máquinas lo que va a interpretar de forma directa con una incertidumbre es esto que está acá, y esto es lo que se representaría en el DSC. Acá nosotros, here in LACOMET, we are developing something like that. Fabio ha estado trabajando con esta parte en el Portus, entonces parte de lo que se va a representar a nivel interno primeramente es esta información que está acá. En forma simplificada. Ok. A partir de ahí, pues vamos a tener una serie de pues, condiciones que nos permiten expresar esta información en un documento que sea utilizable para pues, un elemento digital. With this information, we have all that we need to provide information to the machines. Ok. Trataré de ir un poquito más rápido. Por otro lado, por ejemplo, tenemos aquí ya el uso de un certificado digital destinado específicamente para una comparación desarrollada por el BIPM, en donde se prueba cómo estas herramientas de interpretación de la información se pueden utilizar para que sean leídas directamente. Esta comparación permitió que elementos que leían o máquinas que leían directamente la información pudieran interpretarla con un formato que no es necesariamente parecido al del XML, sino que es aportado directamente por el otro tipo de representación que es más significativo, que es el de metas. En el DSI es importante que tomemos en cuenta, it's important to take in account this. The representation of the information is this one. But this is only the representation, the format, the structure. But we need to provide information with sense. So the idea is to have the digital side, to take the digital side and to represent the digital side inside the DCC. Both are a little bit different, but this information is related, está relacionada una con otra. A partir del 2018, 2019, 19, sorry, the BIPN discussed about the necessity of develop the DSI, so create and approve the draft of the Grand Vision. The Grand Vision o el documento de la Gran Visión propone cómo es que debería establecerse la ruta, o es el documento primario para establecer la ruta en la que se va a representar la información del Sistema Internacional Digital y para qué se va a utilizar. Principalmente está alineado a los principios FAIR, que la información pueda ser reutilizable, encontrable y en general, ya los vamos a ver. Y también que se representen certificados digitales de calibración, que puedan ser utilizados por las máquinas y que pues tengan acceso a todo el mundo. Pues a largo plazo crear herramientas que puedan crear esta información, estos certificados digitales de calibración, y que también puedan leerse. In a long time, the idea is to have some tools to create the DCC and tools to interpret the information of the DCC, because there are no an absolute parameter for that right now. La estructura de la información expresada para los valores asociados al Sistema Internacional Digital tiene esta estructura. Primero están los componentes de valor, los componentes de unidad, las etiquetas y las etiquetas de tiempo. So, for the values that we need to represent in that DCC, but based with the DSI, the structure of this information of the DSI is the values, units, labels, and label for date and time. So we need to relate all the information with these labels of date and time. Idealmente, tenemos dos formas que son aceptables para representar la información de los valores del Sistema Internacional Digital. In the left, we have an permit or not an ideal information. In the right side, we have the ideal information. So we can represent information in XML, but based with DSI right here, using especially this one, the unit. So the unit, in this case, determines the difference. For example, degrees Celsius or Kelvin. What is the ideal representation of the values in the DCC based with in the DSI? This one right here. So the idea is to use all the units of the international system to represent in clear way the information. For example, for humidity, in humidity, we don't use a unit because the humidity is a relative information. So we can represent this information here, but the ideal information is here. For example, we put the one label to represent this relative information. And for pressure, for example, we have here the Pascal, and here the real representation of the information using the SI. Entonces, si tenemos estos tres posibles ejemplos de representar información, el SIM lo que ha estado haciendo en los diferentes grupos de trabajo es discutir este tema. Por ejemplo, don Carlos Galván, que trabaja directamente con el desarrollo del DCC, ha estado preparando a las personas que trabajan en el SIM, en los diferentes grupos de trabajo digital, para que la información sea representada de esta forma, y que en un futuro, cuando se define la estructura ideal para el certificado digital de calibración, esto pueda migrar directamente al certificado digital de calibración. Entonces, el trabajo principal que se ha estado desarrollando en el SIM está asociado a los diferentes proyectos de investigación, pero también se ha desarrollado y se ha trabajado en esta área específica. Cómo representar la información adecuadamente. Vean que también it is important to know that all the date and time labels are right there. Okay. And I think what is in the future, or ¿qué pasará en el futuro? Bueno, tenemos varias consultas o varios temas para discutir. Los task force del SIM están trabajando en el DCC. The task force of the SIM are right now working in the DCC. Yes, this is the answer. ¿Existen países en el SIM con más avances que otros en el tema del DCC? There are countries with more advantages or more investigation in DCC right now in SIM. Yes. The reality is that some countries have a very strong groups for working in this area, and this means this is important because other countries can go to these groups of investigation to try to collect some experiences about that. ¿Existe un único formato del DCC a nivel del SIM? There are a unique format for DCC right now in SIM? The answer is no. There is no format right now in SIM. Is okay? Okay. So the idea is to have a unique DCC format for SIM in the near future, maybe 2025, I don't know. La COMET participa en los grupos de trabajo de transformación digital en el SIM. La COMET participate in the task force of metrology for digital transformation in SIM. The answer is yes, actively, all the time. La COMET está desarrollando un DCC. La COMET is developing a DCC right now. The answer is a little bit not complete right now, because the idea is to use this information to work in a specific area. The first area that we need to work is in mass, and the next one is maybe in dimensional, yeah, length. ¿Existen clientes potenciales para el consumo del DCC? There are clients for the DCC? It's a very good question. Here in Costa Rica, we don't know right now. Inside the labs here in LACOMET, there are a lot of clients for DCC. Maybe we need to ask to the secondary laboratories and to the industry right now if they need the DCC or provide this kind of service. LACOMET aplica el DSI. LACOMET applied the DSI. The answer is yes in all the certificates right now, but these certificates are made for the humans. So in the near future, when we have the DCC, the DSI will apply to the DCC. There are tools for make the DCC? Yes. And there are tools, the last question is, those tools are secure or good? The answer is, I don't know. There are a lot of tools. So we need to review all the cybersecurity that we have inside the laboratories and to limitate the access of the people to the tools that we suppose that are not secure. And that's it. This is all. Thank you so much. It's a very brief revision of DCCs and PSC.
Muchas gracias, don Olman. Thank you very much. I don't know if there's any question, alguna pregunta para don Olman. No. Ok. Perfecto. Entonces, con esto cerramos nuestra actividad. Ya para finalizarla, le cedo la palabra al presidente actual del Sistema Interamericano de Metrología y director del CENAMEP AIP, quien nos dará unas palabras de cierre. So we invite Javier Arias for the closure words of this activity. Thank you. Sí, parece que desde los dos. Okay.
Okay, first of all, good afternoon to everybody. Thank you. First, I won't take you too long, just 5 minutes, I promise. The first thing I want to say is what we just saw over here is, to me, is the reason why we are here, the reason why metrology actually exists. We have seen over here, from the presentation from Mr. Martin to this last one, how metrology is being implemented in different areas, pure scientific like Victoria and Marina, and also Allman presented, and the other areas, how we are through education, the academic or the academy and trainings, as Loreto, who was it? Okay, Nikita, and also Robert presented, how the different RMOs are trying to do different activities to make sure that metrologists all around the world, not just in America, not just in Asia, not just in Europe, all around the world, have different opportunities and areas to become better metrologists for one simple purpose, to actually have a better world. Because the metrological community does not work, as some people think, for metrologists to just make better equipment. That's not the idea of metrology. Our idea is to actually make sure that all the different equipment that you are using measure properly, measure as accurate as possible, so that you receive the better product, the best results, if we talk about, let's say, health, that you can actually have. And that is the first thing. Second, thinking of that, I want to thank all our friends, our colleagues that came from all around the world to be here in America at SIM, at LACOMET, during these 2 days, because we have really achieved really good conclusions, not just for, as I was saying, for the BIPN, for the JCRB, but for the whole humankind. I also want to say thank you to Victoria, who, as you said this morning, maybe this will be, maybe, I don't know if that will be for sure, maybe this will be your last JCRB meeting. So thanks for all the knowledge that you have been giving to the VIP community. And last but not least, I would like to thank La Comet and all the personnel, Fernando as the director, and all our colleagues over here for preparing this little short, I would say, workshop forum. But it was really important because to me it was in 2 hours, we were able to summarize what we did during the JCRB meeting, to bring together what we do as metrologists for humankind. So thanks a lot, and thank you for all, also for all the ones that are still accompanying us during this time, at this time. So thank you. Have everybody a good afternoon, and I hope you can enjoy the rest of Costa Rica, at least tonight or tomorrow morning. Thank you.
Muchas gracias, don Javier. Entonces, con esto cerramos la actividad. So, with this, we close the activity. Everyone, thank you very much. Have a safe travel home. Muchas gracias a todos por estar aquí presentes y nos vemos en una próxima actividad.